Okay, welcome back. So I hope my quizzes are still simple enough. I don't think it's much of a problem, right? So with the practice quizzes and everything, I think that's quite good to keep pace with the material. Please do not underestimate the final though. Just make it a little harder if it comes from different corners and different topics. Ask for a little bit more holistic overview of what is being asked. Some of you are still working. If you're not distracted, you can stay where you are. If you want to sit a little in the back, just go in the back. Good. Final next week on Friday at noon. Those of you who want to take a different date, you really need to work then with the dean's office to get an exception. I'm being asked to make it exactly for that date and time slot. But I'm okay that you take it, for example, on Wednesday when I do it with the F class. Fine with me. But it needs to be coordinated centrally. Good. So any questions to anything that we have discussed so far?
Could you possibly get an extension on the third homework? Maybe just miss the day.
I can't give an extension because it's I need to grade, and I also want to post a solution spreadsheet that you have at your disposition to study and review it for the final. I can't give an extension on that. I also have made it accessible 2 weeks earlier than planned, so it's a tough one. It's also I think it's due next week on Monday, right? So that gives you very little to kind of review the practice and the solution spreadsheet. So short answer is no. Good. Okay, so we're any other questions? We're going to talk today about chi-squared test. So we talked so far basically only about so-called parametric tests that had basically some very solid underlying assumptions that allowed for us to actually use them. So one was a normal distribution. Second one was that they had homoscedasticity. That meant they have equally distributed variability. Thirdly, they had some form of a linear relationship and they were randomly sampled. So now the chi-squared test is the only non-parametric test which we will discuss in this context of our class. And this is basically a test where these assumptions do not have to be met. It's a special class of hypothesis test. The only reason why it's done in this class and not saved for later statistical education is because it is a test that allows the analysis of a scale of a non-scaled or a categorically dependent variable and a categorically independent variable. So when you remember, we basically did now tests, and we will review this on Wednesday. We have the scale independent variable and the scale dependent variable. When you have a situation like that, you will think of either correlation, or if you want to predict a value, you will think of regression. If you have a nominal or categorically independent variable and a scale dependent variable, you will think of as either a set test, if you're comparing a sample mean to a population mean and you have the population standard deviation given, or you will think of t-tests, if you're estimating the standard deviation based on the sample variability, or you will lastly, if you have 3 or more levels on the independent variable, you will use ANOVA that we have done, which either is in between groups and within groups ANOVA, which were the 2 one-way ANOVAs we discussed in this class. So just keep in mind, and the reason why now chi-squared is the only non-parametric test is kind of included in this class is because now we're basically having a third category, a third group where we have a categorically dependent variable and a categorically independent variable. So that also brings us to the next topic. When are you using this non-parametric test? So you're using these when the dependent variable is categorical. So remember, categorical variables, either nominal variables, where they have a name or a label, or an ordinal variable where there's some order involved in the variable per se. When the sample size is small and the underlying population is not normal, you will also think of a non-parametric test, because as soon as the sample size exceeds 30, usually you get away with parametric test if it's not a categorically dependent variable. But usually you can then take this assumption of the normal distribution as given as soon as the sample size is greater than 30. Limitations of a non-parametric test are that the confidence in the effect size measures can be calculated, but they're not easily calculatable as they were in parametric testing. So that's one of the downsides. Also, they have less statistical power, which is mainly associated with the small sample size. Thereby, you're more likely to run into type 2 error. Remember, the type 2 error is the error where you do not see an effect, although there is an effect. So the null hypothesis is to be rejected, but you're not rejecting it for all the factors that are limiting statistical power, with sample size being the most important one. But you also would have variability, sample size, as well as the difference between two groups as being a potential source of the type 2 error. So just to keep in mind, what is a type 1 error, what is a type 2 error? Type 1 error is basically where you're rejecting something that you shouldn't be rejected. That's basically your p-value, and you have an acceptable p-value with which you're comfortable with, that you would accept as a type 1 error. That is your critical value or your alpha. The type 2 error is basically not to exceed 10%, and it's usually estimated prior to actually designing studies by basically calculating or estimating the statistical power. So basically, when you do have a true effect and the null hypothesis is to be rejected, you have a probability of 100%. So the type 2 error is basically that probability, that aliquot, that you will not reject what you should have rejected. The statistical power is 1 minus the type 2 error, and this like this leftover, which is meant to be kept at 90% for the design of randomized studies. This being said, with sample size estimation, you're basically utilizing the relationship between variability difference, alpha, and your acceptable type 2 error to estimate how many people do you need to study, or how many subjects do you need to enroll in your study to actually get an acceptable statistical power. So just keep this relationship in mind. So that was chapter 9. Confidence intervals, and sample size and effect size, I think, and power. Chapter 9 was that. Good. Chi-square tests. Okay, so these non-parametric tests basically come in two shapes or forms. So you have a chi-square test for goodness of fit and a chi-square test for independence. For both, you're testing for an association between the two levels of your variable. So you're testing one condition of your independent variable with the stratifying independent variable. So you have for goodness of fit, you only have one nominal variable. For a test for independence, you have two nominal variables. I will see in a second what that means. So basically, the goodness of fit is a super simple test, super easy, but it follows the same outline as the test for independence. So we'll do first an example of the goodness of fit, and then we do the independence one. The 6 steps of hypothesis testing are the same as we have done in the past. So we identify populations, distribution, and make our assumptions, which there are not many for the non-parametric tests. We state the hypothesis, which is that there's no association between the independent variable at hand and the different levels of that determines the stratification. We determine the characteristics of the comparison distribution, and this is now where it's getting a little different, because now we're dealing with a so-called chi-squared distribution. So this is the next distribution that we're basically, the next comparison distribution that we're discussing. So you have now on your module, module 24 on Canvas, you do have the chi-squared probability table. This chi-squared table basically shows you organized in rows and columns, just in the same outline as we usually had. It shows you degrees of freedom as rows, and it shows you the alphas on as columns. So we have here the degrees of freedom, and here the acceptable alphas. And based on this table, you will determine critical values, calculate and decide. So basically, these critical values are basically somewhere on the x-axis of unimodal positively skewed distribution. And every value exceeding this critical value will again reject the null hypothesis. But the null hypothesis is that there's no association between the categorically dependent variable and the two different levels for the goodness of fit, as we will see in a second. Good. Just remember, it's kind of taking the same shape as the F distribution, right? So it goes in the same direction. Same principle applies. It's a one-sided test on this unimodal right-skewed distribution. So basically what you're doing to approach a chi-squared, and we do example 17.1 to basically illustrate that. So we're matching the frequencies of the observed participants. So we have a certain number of participants. We have a dependent variable in two different levels that we're comparing. We're matching the frequency of the participants expected according to the null hypothesis with the frequencies that we have indeed observed. What does that mean? If you look in Canvas in the example, in the example spreadsheet that I've posted, so there is quite some interesting research out there, and one of these researches is now this example. So there was actually a research group that hypothesized that people born in a certain time, certain months of the year, so rather in the earlier side, somewhere in winter before spring, are more likely to become expert soccer players. It's a timely example now with the World Cup. But basically, so they observed 52 elite players in Germany that were born in January, February, or March. And they found only 4 corresponding players that were born in October, November, or December. So now the researchers hypothesized that there could be something in there. So they wanted to formally test this, whether there's an association. And they came up with all kinds of explanations why that essentially could be the case. And they actually came up with some. The most bizarre one was the zodiac sign. A little bit more of a physiological one was that the mother had less sun exposure and there was some hormonal changes that kind of, yeah, I don't know. I'm not from that field, but it's kind of a more one of the more exotic research questions asked. Good, but basically what we have now, and this is basically what is important to keep in mind when looking at examples like that at your quiz, or also in the real world, if you have examples presented to you in that shape or form. So first you need to operationalize the variables. So what is actually your dependent variable? Your dependent variable is the count of players born in a respective month or in a respective time of the year, right? So you basically, you have early in the year and late in the year. Late in the year as being your 2 levers in your birth period variable. So this is a categorical variable stratifying the whole population into 2 groups. And now you basically have an observation. So you have observed soccer players, and you have early in the year, you have 52, late in the years, you have 4. So that gives you 52 in the first level and 4 in the second. I'm zooming in a bit, but just follow along, because you have 52 and 4 in these 2 groups. So when you observe that, you want to match this now with that frequency you would expect if the null hypothesis were true. So if the null hypothesis is true, and in these 2 levels you don't see a difference, it would be 50% in each level, right? So if you have 52 and 4, that's 56, divided by 2 is 28. So that's your expected count. So that's essentially what you do at the very first step in this analysis. We have 52 and 4 divided by 2 is 28. So this would be what you would expect under a correct null hypothesis. And the rest is simple, because now what you need to calculate is now the chi-squared value that you compare against your chi-squared distribution. And for that, we have a formula that comes on the next slide. And then we just need to make sure that we're meeting all of this. So we have a nominal variable, which we have. We have independent observation. Yes, it's 56 different players. We have a random selection. That can be debated. but let's assume it is. And we have a minimum number of expected participants per cell. So yes, so there's a rule of thumbs what this minimum number should be. If you have very low numbers or 0 entries, you can't do a chi-squared. So the rule of thumb is that you should do, what was it? It should be at least as much as you have cells in the overall table. That should be the minimum number of observations. But there are different rules along these lines. So you will find Nolan and Heinz in the book. They state like at least 2 different rules. I know that there are at least 2 more. But yeah, as an estimate, it should be at least as many cells, as many as you have cells in the table. Good. So now, firstly, we need to calculate. We need to estimate our degrees of freedom. Same thing as always. We're having a number of rows. We have a number of columns. We have k row, which is the number of rows minus 1, and we have k column, which is the number of columns minus 1. The product of multiplying both basically gives us a degree of freedom of chi-squared. So for our example here, we have 2 columns, 2 rows. So df row is 2 minus 1, it's 1. And df column is 2 minus 1 is 1. So 1 multiplied by 1 is 1. So df x2 is 1. It's 1 multiplied by 1. So that's 1. So ironic. So if we just click one further, we have here on degrees of freedom of 1, we have an alpha level of 5% with 3.841 chi-squared. So that's the critical value. That's our guiding stars. That's our guiding star, which we will test against now. So critical value is now 3.841. So, and now we're coming to the actual calculation. And it's simple. It's a simple formula. We know 3.841 is our critical value. Beyond that, we're basically having our p-value or our alpha. And now the only thing we need to do, we need to calculate our chi-squared. And I'm just copying this formula over, just to digest this for a second. So we have observed, expected, and we have a difference between those two. We have those differences squared, divided, and proportionalized to the expected count. So basically all we're doing is it's the sum of these squared deviations referenced to our expected count. And that's simple, right? So if you have observed minus expected, so the O minus E, that is this minus, is this minus this, is 24 and minus 24. Then we just need to square this. O minus E squared is now just the square of this, 576. And referencing this now to O minus E squared divided by E is just this divided by expected. So that's all we need. And now we just need to sum these two up. That gets us our chi-squared. So it's really as simple as possible. It can't be simpler. So we have a chi-squared of 41.14 with a critical value of 3.841. What does that mean? Based on our data, we see that there's significant association in a chi-squared test between the time a soccer player was born and its his or her her time of the year he was born and his performance. So does this really tell us something? Probably not really. So there's confounding in place. There's likely bias in place. So it's very hard to really see any causal pathway explaining that, although the authors tried. So, but again, comes back to the saying that correlation does not equal causation. Good, but this is basically how you would calculate it. So if you're presented with data that is categorical in nature and you have counts within those categories and you want to see whether there's a relationship between the different levels of your independent variable and your dependent variable, which is the soccer players, this is how you would test it. But this is really the simplest of all ways of employing a chi-square test. This is actually, to be honest, out in the real world, you would not see an example like that. You would use a different, simpler test for that. There are different ways to approach this, but it's a nice starting platform to go where we're going next, because we are continuing now the journey into chi-square. We're basically looking at a little bit more of a complex example. So for this example, we have these 6 different steps, and we have now an actual chi-squared test for independence example. And this is a little bit more of an intellectually stimulating example. I actually like this example quite a bit because it also goes towards a topic I feel quite strongly about. Good. So we have, in a recycling study, we have 159 people who were randomly assigned to one of the 3 groups. They had a coffee cup handed to them in a coffee shop, which contained either their name correctly spelled or their name incorrectly spelled, or they had a coffee cup with no name on it. And what they did, they basically would quantify how many of these cups of these individuals would end up either in recycling or in trash. So now think about this through a little bit, because that has a couple of interesting implications when you think about it. On a psychological level, if you see a cup with your name spelled on correctly, are you more likely or less likely to trash it or to put it in recycling? So the idea is it's a very subliminal level, a very subconscious level of basically dealing with customers, but I find it intellectually interesting. And it seems just with the naked eye, there seem to be some differences, and we will look at this later. Okay, so they tested this by taking 159 people, they assigned them in each of these 3 groups, and then they observed what did the customer do with their cup. Good. What we see here is basically out of these 159 individuals. So first, when you look at a contingency table like that, you would first create the marginal totals. The marginal total is basically nothing else but summing them up for each row and summing them up for each column. You're doing that for the simple reason that you just want to understand how many individuals do you have in each of those groups. And how many do you have presenting with a studied outcome. So basically, just to keep in mind in terms of nomenclature, you have the outcome, the dependent variable is either recycling or trash. So this is your categorical outcome variable or dependent variable. This is your categorical independent variable. That's the randomization or the allocation to the respective groups in randomized fashion. So the marginal totals are here adding up to exactly 1/3 of the population for each of these 3 groups. Makes sense, right? Otherwise it would be not a good randomization. So then you have in the outcome groups, you have 52 in the recycling group and you have 107 in the trash group. What does that mean? It means that people are more likely to trash their paper cups, although they're actually meant to recycle them, which is a problem to start with. But now, to sense now whether there's a difference in terms of the different levels of our independent variable, we would now first have to define what is, okay, so if we bring this now in a different format, so we're basically putting this now down in a, so we have recycling. Let's bring this in the long format. Trash. Okay. So now we bring this down. This down. So that's our observed, right? So we have 3 values for observed recycling and observed trash. Now you need to understand what is now expected. Expected, just with our football players, it's basically an equal distribution between the levels of the independent variable. So for our outcome recycling, this would basically be 52 as our outcome divided by the number of levels of the independent variable. So in order to, so you have 3 levels in the independent variable. Your 52 divided by 3 gets you an equal distribution of the outcome that you have observed between those 3 groups. So if there were no association between the levels of the independent variable and your outcome, there should be 17.3 cups in the recycling. In the same fashion, if you would do this now with the trash cups, you would get 35.7 cups in the trash. So it's basically, it's the same exercise as we did with the soccer players, we're doing now with the 3 levels of our respective outcomes. So, and the calculation now is exactly the same. So we want the calculation of our chi-squared. Put this formula right here. But firstly, we want to understand the critical value, and this is still a little bit tricky. So when we go now for degrees of freedom row, we have 3 rows. 3 minus 1 equals 2. So 3 minus 1 is 2. Degrees of freedom column is now 2 minus 1. That is 1. So now we have 2 and 1. Our degrees of freedom chi-squared is now 2 multiplied by 1. So that makes it 2. So degree of freedom from chi-squared is basically if you have 2 degrees of freedom and you're striving for keeping your type 1 error less than 5%, you have a critical value of 5.99. Simple, right? So 5.99 is now the critical value. So, but what do we really see? So we have now observed, let's move this a little down. We have now observed, expected. Now we do O minus E squared divided by E. This is now observed. Oops. Parentheses. Observed minus expected squared divided by expected. And this calculation remains the same for all 6 rows. And the sum of this is our chi-squared. Simple, right? So we have a chi-squared of 7.6 with a critical value of 5.99. We can now reject our null hypothesis, and we can say there's an association between that probability of the cup ending up in recycling or trash as per the 3 different levels of the independent variable. So that's all we can do at this point. We can say there is an association which is significant. And that's all the chi-squared does. It suggests that the null hypothesis that there's no association between these 3 levels and the outcome is basically rejected, and there is an association. So it's basically like a correlation coefficient. It tells you there is an association. It doesn't give you really much insight of what association there is, but it tells you there is an association. Yeah, that's the chi-squared. So now you also want to know any questions on this? I think it's, yeah. This one? Well, let me put it this up. Is it? So it's observed minus expected squared in parentheses divided by expected. So, any other questions?
You said that, like, researchers don't like using this formula, but in my science classes, I use this a lot.
Okay, which one? I said that for the goodness of fit, that there are different methods to use that. This chi-squared is used quite frequently, yes, for if you have more than one lever. If you only have one lever and you're just comparing two groups, there are different ways how you would analyze this. You can do a chi-squared, that's not wrong, right? But there are different ways to approach it. There's a binomial test, so you can use a normal approximation. You can, for fractions and proportions, you can calculate confidence intervals and you can compare standard errors of the mean. You can also approach this with approximations, which you will hear about in further statistics classes. But yes, you can use a chi-squared for two groups only. But if you have more than two groups, then you definitely have to use a chi-squared. Then it's kind of a standard test, yes. But the trick is really, it only gives you one p-value. The one error that I see quite frequently is if you have something like that and you're comparing several groups, researchers would do a priori, they would test each group independently. Because a typical chi-squared test is done on one 2x2 table. So if you have classic example, let's say you have three groups of an independent variable. You have like I don't know, like three levels of some survey or something, and you stratify this as per gender, so biological sex. So you have males and females, and you have three different levels, and you give the frequency count at the proportions. And so one way to do that, or the proper way to do that, is basically calculate one chi-squared on the overall 2x2 table or 2x3 table in that regard. Then you get one p-value, and you basically use that one p-value to kind of prompt or trigger further hypothesis testing. But sometimes what I see is like people just go line by line by line and they compare for each a priori before defining actually an overarching research question. They test each level of the independent variable. It's formally is not correct. So you would first do one overarching chi-squared for the overall 3x2 table before you would go in that. But yeah, it is a common test. So I hope I didn't misstate anything. Now the goodness of fit. So this example where you only have two levers, this is there. The goodness of fit chi-squared is not the only test exists. Actually, there are more suitable tests to do that, but it's not wrong to do it. It's just there are more advanced methods to do that. But yeah, definitely common test. You're 100% right on that. Absolutely no questions there. Okay, chi-square. Any other questions? Okay. So the comparison distribution is the chi-squared distribution, a hypothesis test. So you have chi-squared for independence. The null hypothesis here is that there's no association between the levels of the independent variable and the outcome, the dependent variable. The calculations we have just walked through, we have done that calculation. Critical values we have also found. No, we don't need that. We have done that. We've done this, we've done this, and this. And now we know that 5.99 on our unimodal right-skewed distribution, we have a critical value of 5.99, and 7.6 will exceed this critical value. Therefore, we are rejecting the null hypothesis and we conclude that there are some associations. So one way to look at this as association, which is kind of equivalent to the post hoc testing, is to quantify the adjusted standardized residuals, which is basically the difference between observed and expected standardized to a standard error that is quantified by statistical software. It's a little bit more cumbersome. We're not doing this. So basically, this is, you would get a standardized residual error from the expected counts, so the adjusted residual difference. And also, we're calculating an effect size. The effect size is calculated as Kramer's V or Kramer's V, also called phi. And phi is basically nothing else but the square root of chi-squared divided by the sample size multiplied by the degrees of freedom. So obviously this is easy to calculate. We just need to calculate. So we have now chi-squared divided by the sum of all entries multiplied by our degrees of freedom, which is right here. So, and this by the square root gets us 0.15. 0.15 phi, which is our effect size, gets us in our conventions. So again, there are conventions. So the conventions are now stratified as per the degrees of freedom for chi-squared. Degrees of freedom chi-squared equals 2. With 0.15 would get us to a small effect size in our example. Small effect size. So 0.07 to 0.21 is a small effect size when the degrees of freedom chi-squared is 2. So now you're wondering, okay, so we have talked now about the adjusted residuals, but there's always a different way to look at this. When you have, and for that I'm moving this now a little down. When you're looking here at the different rows, you have 3 different rows, and you basically have, for each of these rows, you have a sum of assigned individuals. And within this sum of assigned individuals, you can calculate the probability of an individual recycling his or her cup or putting it in the trash. And this is calculated as a proportion. And this can be calculated here as a probability or also labeled as a risk. So risk is essentially also nothing else but a probability. So if you calculate now the probability of this this cup going into recycling, this would be a count of recycling as a proportion of the total number of cups in that row or group. So this would be, for correctly spelled name, this probability would be 0.47. If you do the same exercise for an incorrectly spelled name, this probability shrinks to 0.25. If you have no name on it, it's 26%. So what's the implication? If you carry the thought process further, so you want to basically find out if the cup contains a name and your name is written correctly, or the name of that individual is written correctly, is the individual more likely to recycle that paper cup or not? And when you look at these probabilities, that's essentially what we see. Because 0.47 over 0.25 or 0.26 is substantially larger. And one way to calculate this and to relate these two probabilities to each other is relative risk. So it's risk is in this context a little bit of a misnomer, admittedly, but it's basically, it is if it's an adverse outcome like death in a group of patients, you would have this probability representing a risk of death. And if you're relating the risk of death from one group to the risk of death in another group, you get to a relative risk. And just just try to keep this in mind when we're doing this exercise now, because if you take the probability now of correctly spelled name over the probability of having no name on the cup, you get a relative risk of 1.79. And the interpretation of this relative risk in this context, and again, you could calculate confidence intervals around this, and you could do much more advanced, very elegant analytical approaches to that. The interpretation is that when you write an individual's name correctly on a paper cup, he or she will be 1.7 times as likely to put this cup into recycling rather than trash. I don't know about you, but I found that pretty cool, because that has, and from the environmental point of view, that has actually major ramifications, right? Because if you think about it, so nowadays in corporate, in large corporations, changes of that little magnitude have huge, tremendous impacts on a large scale, right? If you have one of our large national or multinational coffee, how do you call them, coffee shops, suddenly put your name on that cup correctly rather than not putting a name on it, suddenly it's more likely that all these cups are actually going into recycling. So that's actually a pretty cool example. I like it. So it has ramifications, and it basically would be an interesting prompt when you think about it, to really test this then also for a corporation, where that corporation could then kind of quantify the amount of recycling that they have produced compared to trash after having such a step change, right? So you suddenly, at day zero, you start putting the name on cups of your customers, and all of a sudden, you basically, the ratio between trash and recycling changes tremendously. And this being said, that also has financial implications, because recycling tends to be cheaper than trash. So this is where all comes together, and this is where statistics is really quite important for all walks of life. That's my point with this. And also, it's from the environmental standpoint, it's actually it's a great example. I like it. Good. Any questions on this? No, it was clear. I think it's a considerably easy test. I think the important thing is that you need to know how to translate what you read in the question into that table. That is going to be key. The arithmetics is just like all the arithmetics we did over the whole semester are considerably simple. It's not difficult. The most difficult one is probably the square root that we have to do for the effect size. So, okay, again, just as a wrap up, so you're building that 2 by 2, 3 by 2, whatever number by 2, or by whatever other number table. And once you have this table, you calculate the marginal totals. Marginal totals, so those of you that go further into stats, marginal totals, marginal probabilities, this is what's being discussed. The marginal totals are basically the sum of the respective rows and the sum of the respective columns. The marginal probabilities are these. That's basically just calculating one probability out of the other. Usually it's quite easier with recycling and trash, it's not as clear cut, but if you have as the outcome of interest, you have death or hospitalization, it's quite logically which probability you're going to calculate. Good. Then you come from knowing the observed numbers. You're just rearranging them. You calculate the expected numbers. The expected numbers are considerably simple to calculate because you have the marginal totals. You know from the outcome, you know the marginal totals. You can calculate all of these quite simply and fast. Particularly in a randomized setting, it's not a problem because they are equally distributed amongst these groups. If these groups are not equally distributed, it's a little bit more complicated because then you need to calculate the probability from the marginal totals. And this is now plural because here they were equally distributed, was simple. If they're not equally distributed, you basically need to take the probability deriving from both marginal totals. But that's yeah, nothing we need to discuss now. But it becomes a little trickier with differing numbers. All right, good. Then once you have the chi-squared, you can test against the critical value that you determine with the degrees of freedom. Once you have the chi-squared, you can easily also calculate your phi, your effect size. That's when you know how strong and how insightful your analysis essentially was and how strong that effect is that you're observing. And then with probabilities and calculation of relative probabilities and relative risk, you can then be more specific in your tested observations. Of note, relative risk, you can literally do hypothesis testing with this. You can, if you want to know if a relative risk is significant or not, there's a formula that basically takes into account all aspects and row numbers of that tested relative risk, allows you to quantify a confidence interval. And as we know from the confidence interval, if you remember from the paired sample t-test, if the confidence interval overlaps 0, it's not significantly different from before to after. If you have a relative risk and you have a confidence interval that overlaps 1, your relative risk is not significant because it's not significantly different from 1, where 1 is basically the probability of A is equal to the probability of B. So the 95% confidence interval exceeding 1, the lower end exceeding 1, or the upper end being less than 1 for a protective effect indicates that there's a significant effect on your risk by whatever intervention you're testing. But more about this probably in later statistical education. Okay, any questions on this? Okay, we have 9 more minutes for, and I'm sure you were looking forward to it. We're doing a little R. So I have a little R script that basically, just for the sake of completeness, I have included this with the this class. Again, I'm treating R as an add-on, as for you to get comfortable with these kind of tests in R, that you also expand your kind of portfolio of things you have at your disposition in addition to the Excel spreadsheets. You have here the recycling example in R, and if you run just line 1 to 4, you're basically getting as the output exactly that table that we have just developed in Excel. You get now, if you run line 6, you get labeled as X2 and chi-square object. So chi-squared in R is basically run with chi-sq.test of that table that you have provided to R. And then you can run here your object, you're packing it in X2 as an object. Once you run that object, you get all these dimensions of that test. So you get your chi-squared of 7.6, you get your degrees of freedom, and you get your corresponding p-value, which we know was smaller than 5% at an effect size of 0.15. You get more out of R. You can hypothetically also extract all of these parameters. So you get data name, you get the expected out, you get the observed out, you get p-values out, you get parameters out, you get residuals out, which is important. That's observed minus expected, and you get the standardized adjusted residuals out. The standardized residual, yes. No. This is on the module. It's in-class code R. If you go on the chi-squared, it's here the third entry on your module.
Does it have a submission box?
Hmm?
Do we need to split?
No, you don't need to split that. This is just for you that you have to code for the sake of completeness. No, so the reason is just The reason why I included it, that you have that code, that you know how to do a chi-squared in R, and also because Norn and Heinz now only scrape over the adjusted residuals, and here you just get the adjusted residuals quantified. So if you run here line 7, you get here the observed count. You get on line 8, you get the expected, just like we calculated them. With X2, you get the so-called residuals. Where the residuals are basically, it's the difference between observed minus expected over expected. And you get the standardized residuals. And with the standardized residuals, you essentially, you see already these differences that you have for recycling. So you see tremendous differences between recycling between the other two groups. And that kind of points you already towards that direction that there's a difference. So what this is, yeah. So this is basically a chi-squared in R. The key again is just to put the data in the right format for in your table, that you can actually run that line. The function of chi-squared will basically need, it will ask for a table, a matrix arranged exactly in that format as we have arranged TBL here. So it needs to look in that format. Okay, any questions to anything in R? Any questions to anything in Excel? That was the last calculation for the semester. You're off the hook. Okay, good. Thanks so much. That's everything I got. Yes. Preferably both, yeah, but you can also make the notes in Excel and fun with that too. If it's clearly visible, if I have to look at it at line X 2417, I'm not going to see it. So just put it in an organized fashion that I can find it easily without scrolling like a million times, then it's fun. Yeah, you're welcome. Also, I posted an announcement. Please review the effect size announcement for ANOVA. So there is a question, and one of your colleagues has pointed it out to me. There's a question asking for a symbol for the effect size in an ANOVA. The R square is also labeled as eta squared, and you will see that in the PowerPoint. It's not a big deal. I mentioned it when we did the class, but it's not in the slides.
So Wednesday's review.
Wednesday's review, yes.
So
Yes.
for the doc, we just put like
For the what?
like if we do 2 separate documents that we
Yep.
hand in, you want us to just write the answer to the doc of like.
Yes, preferably just put it in a Word document. Yeah, just in a nice overview, and then I can see you have the calculations in the Excel. And,
So if I put like a full sentence answer, like I don't understand.
well, I guess some of the questions do ask for full sentences. Yeah,
So then if I put that just like at the bottom of like my.
that would be
in the Excel,
exactly, yes.
that'd be okay.
That should be fine. Yes, if I can find it easily.
Okay.
Don't make it hard for me.
Not gonna put it like at the bottom.
Exactly, please not. All right, thanks.